The Doppler effect is shown when a fast-moving object appears to warp wavelengths such that they can appear longer or shorter than they actually are. That's a lot of complex words, so I'm going to explain it doing a graph here. So first, I'm going to plot points that a car's movements would be. So for instance, this car is going to be moving a ½ inch per second. So to use this ruler, I can start at like 4 inches and put one dot there. And then our second dot, so a second away, is going to be at the 4.5 mark. Then our third second, or a third point, is going to be at the 5-inch mark. So basically right now, each of these dots is 1 second apart, and our dot is moving at a ½ an inch per second. So what we can do is in this graph, our speed of sound, or speed of the wavelength, will be 1 inch per second. So what we can do is this point right here is going to be our latest point. So this point literally just happened. So it's going to be our point 1. Then this point happened a little bit earlier. So this is going to be our point 2. And then this third point is going to be our point 3. So this point has existed for 1 second, this point has existed for 2 seconds, and this point existed for 3 seconds. Well, this point existed 1 second ago, this point existed 2 seconds ago, this point existed 3 seconds ago. So now what we can do is we can take a point, we can take this first point here, we can line it up with the 5-inch marks, and then we can say, okay, this point has existed for 1 second, and we know that our wavelength is moving at 1 inch per second. So we can then see that 1 inch away, or how long this has mattered for a second, our wavelength has moved an inch away. So that's our first wavelength. But since wavelengths go around in all directions, we also have to do something at this 4 point. This does happen to intersect with our third point, but at this point it doesn't matter. Then we can do the same thing with our second point. I'm using colors to better represent which wavelengths are for which points. So for our second point, this has existed for 2 seconds. So the wavelength have enough time to move 2 inches away. Because it's existed for 2 seconds, it's had 1 second to go 1 inch and 2 seconds to go another inch. So we can draw a wavelength there at our 6 inch. Now we can also do it at the other end. So we can do it at our 2 inch interval. Now we can do the last thing for the last wave, or last point. So we can do the same thing where we line it up with the 4. And since this existed for 3 seconds, it can now move 3 inches away. So it'll be ending up at our 7 mark here. And we have to do it the other way, so we can put it at our 1 inch mark here. So now you can see as our dots are moving in this direction, the wavelengths, or the lengths between these waves, is a lot shorter than it would be here. But in reality, what the wavelength is for this is whatever here to here is. But that isn't what we're showing here. If I was standing right here, and I was looking at these wavelengths here, I could see a higher wavelength because they're closer together. If I was standing at the other end, I would see a lower wavelength because they're further apart. This is what the Doppler effect is. As an object moves faster, these wavelengths get closer and closer together until, for sound, if you start moving the speed of sound, you create a sonic boom. These wavelengths start crashing into each other. They're all on top of each other, and it just creates a massive shock wave. That's what a sonic boom is, and that's why the Doppler effect shows how that happens.